In a previous video, we looked at the flying V, the radical Dutch concept that promises to cut fuel consumption by 20% and how they might be losing the race to American-based manufacturer Jet Zero. But while the aerodynamics are brilliant, hundreds of you pointed out a massive problem in the comments section: physics. Specifically, how human bodies will react when you put them inside a giant flying wing. The Flying V is the most exciting leap in commercial aviation design since Boeing drew a tube with wings in the 1950s. It promises to slash fuel consumption by 20% and fundamentally reimagine what flight looks like. But buried inside that elegant, sweeping silhouette is a structural engineering problem that could keep it grounded forever. We are talking about the physics that want to kill this aircraft before it ever carries a single passenger: ballooning flat surfaces, catastrophic stress concentrations, and the uncomfortable reality that the very shape making this plane beautiful is the same shape making it nearly impossible to build safely. To understand why the Flying V matters, you need to appreciate how stagnant commercial aviation design has been for 7 decades. Since the Boeing 707 in 1958, the fundamental architecture has not changed. A long cylindrical fuselage, wings bolted to the sides, engines beneath those wings. The whole assembly punches through the air with considerably more drag than engineers would like, because the tube-shaped body is not particularly aerodynamic. It is simply the most structurally convenient shape humans could build at scale. The Flying V, conceived by designer Justus Banaat and developed extensively by researchers at Delft University of Technology in the Netherlands, throws that compromise out entirely. Passengers sit inside 2 diagonal channels that form the legs of the V shape, and the entire aircraft generates lift across its full span. Every surface is working, nothing is dragging through the air, doing nothing. Wind tunnel testing confirmed a lift-to-drag ratio improvement sufficient to support that 20% fuel reduction figure. In an industry where a 2% efficiency gain is considered a major commercial victory, 20% is the kind of number that makes airline executives sit up very straight. But here is where physics begins its counter-argument. Every pressurized aircraft cabin is a pressure vessel. At cruising altitude, the ambient pressure outside is roughly a quarter of what it is at sea level. The cabin is maintained at pressure equivalent to about 8,000 feet, uncomfortable but survivable. That difference, around 8 pounds per square inch, sounds modest. Multiply it across the entire interior surface area of a wide-body cabin, and you are talking about thousands of tons of outward force pushing against the walls, floor, and ceiling at all times. For a cylinder that is manageable, for a flying wing with flat walls, it is a structural emergency waiting to happen. Nature does not build flat pressure vessels. It builds spheres and cylinders. When you pressurize any container, the gas inside pushes outward in every direction simultaneously. And the geometry that handles that load most efficiently is one where every point on the surface experiences the same tension. A circle achieves this. A flat wall does not. This is called hoop stress, and it is the foundational reason every pressurized passenger aircraft you have ever flown in is shaped like a tube. Think about, let's say, overinflating a cheap rectangular pool toy. The corners stress, the flat faces bulge outward, and if you keep going, it fails at the weakest point, which is almost always a corner or an edge, where the geometry changes and stress concentrates. Now scale that up, give it 8 pounds per square inch, acting on thousands of square feet of surface. Give it 600 flight cycles per year, each one pressurizing and depressurizing the airframe, fatiguing the material incrementally with every single cycle. The history of aviation is, in part, a history of pressure vessel failures. The Havilland Comet, the world's first commercial jet airliner, suffered catastrophic in-flight breakups in 1954. Investigators traced the failures to stress concentration at square windows, corners where hoop stress could not distribute smoothly, leading to fatigue cracks that propagated until the fuselage tore apart at altitude. That investigation reshaped every assumption about aircraft structural design, It is why every commercial aircraft still uses oval windows today. The Flying V faces a version of this problem that is significantly more complex. The passenger cabins are elongated, roughly oval cross-sections embedded diagonally into a blended wing structure. The junction between pressurized cabin and unpressurized wing creates geometric transitions where stress cannot flow smoothly and instead concentrates at the boundaries. In computational stress modeling, these junctions light up like warning flares. And under sustained pressurization, flat or gently curved surfaces bow outward toward their natural equilibrium geometry, a sphere. Engineers call it the pillow effect. An aircraft cabin that visibly deforms under operating pressure is not one you can certify, and it is not one your passengers will feel comfortable sitting inside. The instinctive fix is to make the walls thicker. That approach was tried in early design iterations, and it was self-defeating. Add enough material to resist the hoop stress directly, and the aircraft gains so much structural weight that the aerodynamic efficiency advantage evaporates. You end up with a very expensive, very heavy aircraft that flies no more efficiently than the tube and wing it was meant to replace. The breakthrough came from moving the structural work inside the airframe entirely. Instead of making the outer walls strong enough to resist the outward pressure on their own, you accept that the pressure exists and you install internal elements that counter it from within. A system of vertical tension struts running between the floor and ceiling of the passenger cabin acts as structural tendons. The floor wants to bow downward under pressurization load. The ceiling wants to bow upward. The struts hold them together, keeping the geometry stable without requiring the outer skin to carry the full burden. Working alongside this is an advanced carbon fiber ribbing architecture running through the interior of the wing body structure. Traditional aircraft use frames, structural rings that carry loads into the skin. In the Flying V, because the cross-section is not circular and varies continuously along the length of the cabin, the ribbing must be non-uniform and carefully tuned. Different sections experience different stress profiles depending on where they sit relative to the wing's lift distribution, fuel load, and pressurization loads. The ribbing is designed not simply to be strong everywhere, but to be specifically strong in the right directions at each location. The result is a wide-body interior achieved without the weight penalty that earlier analysis suggested was unavoidable. The internal skeleton approach achieves adequate structural performance with significantly lower mass penalties, keeping the fuel efficiency case intact. Recent scale model pressure testing at TU Delft confirmed that the internal geometry designed to manage pressurization loads performs within predicted parameters under realistic cycling loads. Modern thermoplastic composites are what make this skeleton buildable. Unlike traditional aerospace composites cured in autoclaves, thermoplastics can be heated, reshaped, and welded rather than bonded with adhesive, producing joints that are lighter and more damage tolerant. They're also compatible with additive manufacturing, allowing complex, topology-optimized structural shapes that would be impossible to produce by conventional machining. And embedded fiber optic strain sensors laminated directly into the composite airframe monitor microscopic stress changes in real time throughout every flight, shifting structural integrity management from periodic inspection to continuous awareness. Solve the pressure problem, and you still have to solve what happens to your body while you sit inside the aircraft. In a conventional tube and wing aircraft, passengers sit close to the aircraft's longitudinal axis, the center line around which the plane rolls during bank turns. The distance from your seat to that axis is relatively small. When the aircraft banks, you rotate gently with it. In the Flying V, passengers in the outer seats of the V's diagonal arms are seated far from the aircraft's center of mass. The lever arm is large. When the pilot banks the aircraft, those outer passengers do not merely rotate, they physically rise or fall several meters relative to the center, generating vertical accelerations a conventional aisle seat passenger would never experience. The effect is directly analogous to a seesaw. Sit near the pivot, and you barely move. Sit at the far end, and small angular changes translate into large vertical displacements. In turbulence, or during a routine banked approach, passengers in the outermost seats experience heave forces meaningfully higher than those at the aircraft's center. Critics have taken to calling it the vomit comet problem, and it is not entirely unfair. TU Delft's response involves two measures. First, refining the cabin positioning within the wing cross-section to place occupied areas as close to the neutral bending axis as the aerodynamics allow. Second, active ride smoothing through fly-by-wire control systems that dampen the aircraft's angular response to turbulence inputs before passengers feel it, similar in concept to the active suspension systems used in modern high-performance road cars. Both measures help. Whether they help enough to produce a passenger experience that airlines can actually sell at competitive prices is a question that only full-scale flight testing will definitively answer. This is precisely where the American competitor JetZero is gaining ground. Their blended wing body design is, by comparison, deliberately conservative. The shape is less radical. The cross-section is closer to cylindrical. The pressurization problem is more manageable, and the lever arm effect on passengers is less severe. JetZero is building an aircraft that regulators can evaluate against existing certification frameworks. The Flying V may require entirely new certification standards to be written around it. The Flying V is not science fiction. It is a collection of engineering problems, and engineering problems, given sufficient ingenuity and the right materials, get solved. The pressure vessel challenge that once looked like it would ground the concept permanently is now a solved problem in principle and an advancing one in practice. The structural skeleton is designed, the materials are maturing, the scale models have held. What remains is time, testing, and the question of whether an aviation industry that moves slowly by necessity will commit to something this radical when a more conservative alternative is already taking shape. So here is the question I will leave you with. If the engineering delivers, if the ride smoothing works, if the cabin holds pressure across 30 years of service, and the ticket in the outer roller coaster seat costs 50% less than the equivalent on a conventional wide body, do you take it? Or do you pay full price to sit near the center line? Let me know where you land in the comments below, and I can't wait to read all of them.